today and in next 2 lectures we are going to discuss some elementary geometric algorithms. Let's first begin with some basic ideas. Let's suppose we have a point in some space d-dimensional space D, RD. We have 2 points P and Q. Then this segment is defined by alpha P plus 1 minus alpha Q, where alpha varies anywhere from 0 to 1. If we remove the restriction given here, then this describes the entire line passing through these 2 points. If we have several points P1, P2, P3, P4, P5, then the same expression where we express alpha 1 P1 plus alpha 2 P2 alpha n Pn, say we have some endpoints. This spans a space. If we don't put any restrictions on alpha, then it spans the space described by these points. So, if we have some origin with respect to which we have these vectors, if we restrict ourselves to such a constraint, on the other hand, over here we had, so each of these alphas are non-negative and the sum of these alphas is 1. This is equivalent to this constraint. Then it describes a convex region defined by these points. Say if we had these points, then this entire region is spanned by this expression. Now, such a region is called a convex region, and that is because you pick any 2 points and you consider the segment, line segment between them. This entire segment is inside this region. So, this is called a convex region. So, a convex region defined by n points in RD is given by this. The surface of such a convex region is called the convex hull. See, the convex hull of a set of points is the surface of the region let us call it x, which is alpha I Pi, where each alpha is non-negative and the sum of alpha I is 1. Now, in many applications, one would like to compute the hull of a set of points. Today, we are going to discuss efficient algorithms to compute hull in 2-dimensional space. It is indeed much more difficult in higher dimensions, but in 2-dimensional case there are several very efficient algorithms. So, our problem is convex hull of a set of points P in 2-dimensional space. Now, there is one small problem that we will need to solve often, which I am going to just state here. It may happen that we have a point P1 and point P2, and there is a vector P2 minus P1. So, these are currently points in two dimensional space. Then we may want to know whether the position of P3 is to the left of this vector or to the right of this vector. So, one possible way is to compute the cross product of P2 minus P1, P3 minus P1. And if we think of this as a xy plane, and in a right-handed coordinate system, the z is coming out of the plane. In that case, this vector will be pointing towards positive z axis if this is to the left, and it will be pointing towards the negative z axis if it is to the right. This actually will be, so suppose the two coordinates of this are u1 comma u2 and v1 comma v2, then this would be u1. So, we have a I j k. So, u1 v2 minus u2 v1. It is important in geometric problems to try to solve problems with minimum amount of errors due to computations. The reason is that often the quantity that we compute loses its meaning because of the errors. For example, if somebody wishes to compute the intersection of two polygons, then it is inevitable that you will have to compute these two coordinates, and that may result into errors. And if you end up getting a point somewhere here, then the polygon that you will compute will not be contained completely, and maybe here is the other point. So, what turns out is that the intersection that we have computed is neither inside this nor inside this. So, one would like to ensure that the point that we compute is approximated, if not exactly here, but inside this, and so on. But more than that, a problem such as this, which has yes or no answer, is the direction of this arrow towards the left or towards the right of this, one should ensure that one does not compute any expressions which may have errors in deciding the answer. Anyway, coming back to our problem of convex hull. We are now given a set of endpoints. The algorithm that I am going to discuss is the one that I am going to discuss is called Jarvis March. The basic idea behind this algorithm is the following. Imagine that this is a plank and you have put nails on these points. Then all you need to do is wrap a string around it. If you do that, you are going to get this shape, that will be the hull of the convex region formed by these points. And this is exactly we will like to capture. Now, if I take a horizontal line at minus infinity, y equal to minus infinity, and bring it up, then it is going to hit the lowest point. If there are more than one lowest points, then pick one with the minimum x value, and let us call that point P naught. P naught is the point with minimum y coordinate and among them with minimum x coordinate. Now, such a point has to be on the hull. The reason is that if we choose a suitable line, we can separate this point from the rest of the set of points. If we can separate this point from the rest of the points, and that is possible with this particular point P naught, then we notice that no amount of combination of these points can express this point. Okay. The combination that we have described here earlier is one in which we have alpha I Pi. So, the convex hull of the rest of the points is bound to be excluding this point, the hull, because we have this region which contains all the points. So, the hull must be inside this region. So, if we include this, the hull must change, and if the hull changes, then this must be on the hull. So, we begin with a point a priori known to be on the hull, and our idea is to traverse through the potential points which should be on the hull. And to do that, essentially what we have done is we started with the string and tied it with this knot, nail, and then we locate. Suppose we stretch it and we try to find the first point that will hinder this string, that will come and will hit this. Once we find this will be the next point, and then we will repeat the process. Now, we take this line and try and move this way, it will be hit by this one. So, we will have string going like this, then we will try and move it to this way. So, how do we find these points? Well, so now we began with this point which we know is on the hull. Now, we are going to start with a reference point P. So, our first point is P naught, and we are looking for the next point here. So, we are going to iteratively do this search for these points until we come back to this. So, the process will be that let us repeat these steps. In these steps, we are going to look for a point which is to the right, the vector from P naught to which is right towards the right of everybody else. Notice that the entire set of points are on this half plane. So, we will take any point Q, let Q be select from p minus p. We pick any point from this set, and then for each x in the set p minus p comma q, p minus p, do. If x minus p is to the right of q minus p, that means we happen to have found an x here, then I would make this q, because this is now a potential next point for us, then set q to be equal to x. So, after this for loop is over, we must have found this point as our q. So, we will then say output p and set p equal to q, and we repeat this process until our p naught is equal to p naught. And I think at the end we are going to output the last one. Well, that has been already done, so we will. So, this would complete the entire process. Notice that this test takes order 1 time, hence the for loop costs us order n, n being the size of the point set. Now, if the hull has h points, okay, if the convex hull has h points on it, then the complexity will be order nh. This algorithm will be efficient if the number of points on the hull are much lesser than the total number of points. For example, if you happen to have several points in the set, but very few points actually end up deciding the hull. In this case, the hull is decided by just these 4 points, while there are several points over here. The cost will be relatively low in computing this hull. Now, let us go to another algorithm, and this is known as Graham scan. Now, in this case, without loss of generality, we will assume that all the points are in the first quadrant. Here is the origin of the coordinate system, and we have various vectors to the points. So, in this case, the first step we are going to take is to sort. Once again, I forgot. What we have to do is select this origin as the point which has the lowest y value, and among them, if there are several points with the same y value, then the minimum x value. So, I am going to choose this p naught exactly the same way that I chose in the other algorithm. So, this is one of the points of the hull, and then the rest of the points will be in the first quadrant. It is possible that some of them are on the axis, but they can be here, of course. In this case, I must apologize, it is not necessary that they are in the first quadrant, but they will be in the first and the second quadrant. So, we sort these vectors in the increasing angle that they make with the x axis. So, let these be P1, P2, P3, P4, P5 and so on, Pn. So, sort vectors Pi minus P naught in increasing order, of the angle they form with the x axis. So, once again we know that this is on the hull, but what is more, we also know if this is the rightmost the first one of the points in this order, then this entire line this straight line is such that all the points on the one side of this line. So, once again you can imagine when you are wrapping, this point must be on the hull. So, this second step is to put P0 and P1 in a stack. So, we push in the stack P0 and we push in the stack P1. We will use this data structure and eventually all the points of the hull will remain in the stack. So, we have at the moment P naught and P1, and then we move on to the next point. So, we will put P2 here. Now, what we have to check is that if this is P naught, this is P1, then P2 must be to the left of this direction. If P2 were on the right of this direction, in case of P2 obviously not possible, but subsequently such a situation could arise, then this cannot be a convex polygon in one place. So, that is not possible. So, we will have to eliminate that. From now on, we will iteratively put a point and verify whether it bends properly towards the left. But what happens if it bends to right? So, let us try and look at that case. Let us suppose we have a situation where we have at the top of the stack this one, subsequently these points are in the stack, and we have been computing the hull. And then the next point we find, remember the points are sorted in the angle in this way. So, the next point, let us say and maybe since P naught is at the bottom, I will assume we have these 3 points, and the next point let us say is here. So, with respect to P naught, these are increasing angles. So, it is perfectly possible that the next point is here. and then we put this in the stack. So, we find that with respect to this direction, the new vector. So, let this be say p I, this is some p j, the previous one, this is p k even before that. With respect to direction p j minus p k, the direction p I minus p j is to the right. Hence, we cannot accept this situation. We will remove p j and consider now this Hull. Now, imagine that this appears to be a straight line. Maybe this is still bending here, and this is my p j. This is still bending to the right. In that case, I am going to again remove this and connect directly to the one before it. So, what may happen is that we lose some of the points which were earlier part of the Hull. So, in this iterative process, each time we are going to insert the next point and verify whether it makes the right angle. If it does not, then we are going to remove, starting from the top of the stack, one point at a time, and verify eventually that the bend is correct and stop there. So, let us try and capture this here. So, for j equal to 4 2n 2, one at a time. I am assuming that after sorting the vertices are labeled in that order. So, after sorting, these are in order p. After p 0 we have p 1 p 2 in the increasing, the indices are accordingly as per the sorting. Yeah, I am sorry, should be 3 2n minus 1, because we are using p naught. So, we have labels 0 through n minus 1, p n minus 1. Okay. So, what we will do is, while now I am assuming that whatever we have in the stack is properly well, maybe we can just start with 2. So, let us just start with 2, because it is possible that the very first bend is p 1 p 2. Okay. So, this is all right. We have put 1 inside it, and now before we put 2 or the next point, we will check, while check the condition. Well, we need to give some label to those. So, let us say x is top of the stack and y is second from the top of the stack. We have these two. So, right now we do not have p 2 in this, we have x here and y here, these, and we check if the bend from y to x. So, we have y x and then we have p j. So, x minus y vector is to the right, to the left of p j minus y vector, then we have to remove this. So, we will say if x minus y is to the right of pj minus y this is the condition. Then pop S. But we have to do this iteratively. This has to be repeatedly done. Yeah. This is y. Oh, sorry, pj minus x. This is pj minus x. This step has to be done repeatedly until this condition fails to happen. Oh, okay. We have x minus y is to the left of this. Is to the left. If it is to the right, then this is okay. If this is to the left, we must pop the top of the stack. We got to remove this. So now we have to do this iteratively. So we will have to put this in a loop. So let's just put this entire process inside a loop, and then we are going to have while x minus y is to the right of pj minus y x do where first remove the top of the S and then compute x as the new top of the stack, y is the second of S. Once we are done with this, the fifth step is to push pj into the stack. So the entire search, so this search here ends at x, y and the pj. Then we will continue. So the for loop will then search for the position for the next one, and this process will go on. Finally, in the sixth step, output the contents of the stack. The algorithm in the first step, in the step 1, involves sorting of n elements. So it costs us order n log n. Now let us look at what does it charge in executing this for loop which contains this while loop. Now on the face of it, it is not clear how long this while loop will run. But then there is one obvious fact that we can see, that once a point leaves the stack, it's one of the earlier points than pj, the one that we are computing. Any of the earlier points never enter the stack. Notice that this is the only way it enters the stack. So subsequently pj plus 1 will enter and pj plus 2 will enter and so on. So any point will enter once and will exit at most once, because it is not going to enter again. So the cumulative cost of all the pops cannot be more than order n. Cumulative cost of all the pushes will be order n. Hence, the step 4 and step, okay, I think I have to, so this is inside this for loop, I would not name. So, this is push S Pj, this is inside the for loop, and I would make this step 5. So, the total cost of this step, so step 4 is going to cost us order n. Hence, the total cost is order n log n. See, unlike, well, this is taken over by this is the dominating term. So, the total cost is only n log n. Unlike the previous algorithm, the cost here is n log n, it is independent of the number of points on the hull. So, this can be more profitable in case there are several points on the hull, where the other algorithm will not be very effective. Now, I am going to also give you one incremental algorithm. Yeah. While this is to the, I keep making this mistake. So, yes, this should have been to the left, because this is what we do not want. Right. Okay. So, let us now talk about an incremental algorithm. In this case, we are going to build a hull one point at a time. So, let us suppose you have a hull made up of, say, first j points. Say we have points p1 through pj. If point pj plus 1 is inside the hull, then it is not going to modify. The hull will remain intact for the set p1 through pj plus 1. But in case pj plus 1 is outside the hull, let us say it is here, then we have to see which all sides that are visible from pj plus 1. So, this is visible and this is also visible, but these are all hidden. So, if I draw a tangent, it will touch these 2 points, and then we are going to remove this portion. That will form the convex hull for the first j plus 1 points. Then, of course, if I find, now it is, let us say, for the sake of a more general case, say this is pj plus 2. In this case, the visible edges are these 3. So, the hull will be formed by connecting these 2 vertices with pj plus 2, and we will be removing these edges. So, this is an incremental algorithm. What does it involve is to identify one visible edge. So, let us suppose you have a hull and first thing we have to figure out whether the point is inside or is it outside. If we find that it is outside, then we will have to figure out one edge which is visible from the new point pj plus 1. So, we figure out this edge or a vertex, which is by visible, which means that this line segment does not cut the convex hull, the current hull. Then we have to go on walking until the point that we go to is the last point from where we can see this Similarly, you have to walk on the other side and do the same thing. So, there are two parts to this entire process. One is to find first point which is visible from the new point, and two, scan through this on either side of this point, find out what is the last point which is visible from here and the last point visible from here. Now, there are several ways to do these, but I am going to just discuss one of them. Suppose we sort the set P in increasing order of x value, increasing x value or x coordinate of those points. So, we have points and so on. So, suppose we have found the hull of these points. Then observe that say this is the last point P j and this is P j plus 1. In this case, notice that always P j will be visible from P j plus 1. The point which is next to P j to its left must be visible from here. The reason is that if I draw a straight line from here to here, that line cannot cut through this the rest of the hull, simply because everybody else's x coordinate is less than or equal to the x coordinate of this. So, this quickly sorts out the first part of the problem of finding out the first visible. Now, as we walk, as we go on one of the sides, we have to now determine whether this is visible from here or not. So, how do you figure that out? It can be what happens when it is no longer visible. So, when we come here, what we notice is that the bend that we have, this line segment and this line segment, as long as this line segment from here is to the left of this line segment, this is okay. But the moment here what we find is this line segment is to the left of this line segment, we say it is no longer visible. This is not visible from here. So, it takes an order 1 time to decide each of these vertices whether they are visible from P j plus. As we walk along, every point that is found to be visible, we move on. We have to move up to this point, which is the first point which is not visible. So, if we find k points which are visible in this entire segment of the hull, there are k points, then we are going to test k plus 2 points for visibility, one more from each side and this one. We are going to test k plus 2 points. Each time we are going to delete the k minus 1 line segments in between them, the k points which are visible. So, there are k minus 1 segments which are in between, and we are going to introduce 2 new line segments into it. So, I am not going to explicitly write down the algorithm, but let us try and analyze this algorithm. We notice that in each step we are going to introduce at most 2 new line segments. If the point is inside, we are not going to introduce anything, else we are going to introduce 2 new line segments at most. So, we can introduce at most 2n, well, 2n new line segments, lines into the hull. So, the number of lines that we can delete from this entire process cannot exceed what we introduce into this. So, the sum total of tests that we do for visibility will be the sum of these k's, and the sum of k I minus 1 in ith step, if we have eliminated, if we have found k I visible vertices, then we have eliminated k I minus 1 lines from it. So, this sum has to be less than or equal to 2n, because that is all we introduced. Well, initially we actually form a triangle, so there will be one more. Hence, this sum k I is less than equal to 2n plus n, the sum 1 over n, 3n. And we do k plus 2 tests in each step. So, this adds up to, the total cost adds up to, and the 2 each time. So, the total cost is 5n, order 5n tests we will do for visibility here. So, the total cumulative cost will be order n. But there was an initial cost of sorting. So, this plus order n log n, and hence again this incremental algorithm will cost us order n log